Hey everyone, this is Belinda Carr. Welcome back to the Boost Easy podcast, where we dive into the world of construction and explore the stories of people and companies who are shaping the future of our industry. We've got yet another exciting podcast for you today. I'm speaking with Jarrett Davis, building scientist at Built Environments. Thanks for joining us, Jarrett.
Absolutely. Thanks for having me, Belinda. I really look forward to our conversation.
Yeah, I love your setup, though. Very professional compared to all the other Zoom calls I've had in the past.
Yeah.
Yeah. So we met in Bryan, Texas earlier this year. I think a month or 2 months ago. No idea. 2024 is flying by.
Right.
But your company invited me to watch the fire testing of some magnesium oxide panels. And it was very cool, very dramatic. I had never experienced one of those before, so as a first time experience, it was very educational but also very dramatic.
Yep.
We'll definitely dive into all the details of that fire testing later on in the podcast, but let's start off by talking about you and talking about Built Environments. For people who haven't come across the company before, what does Built Environments do?
Oh, that's a loaded question. Built Environments, really Built Environments is meant to help other folks that want to get in the industry break that barrier. We do innovative testing, and not just the testing that is required for code and the requirements just to get into a usable material, but our goal is to help an innovator. Most of our innovators that are developing products or bringing products to market don't know how to do it. And a lot of our process is really helping them walk through that process in an efficient and costly manner, in an correct, whatever that word was, in a manner that it can help them, because it's very expensive to bring a product to market. And it can be
extensive and a lengthy process too.
It is. But we've kind of, we've done it from a personal aspect. I've done it from products that I've invented and brought to the market, as well as from other manufacturers and their products. And we have a lot of manufacturers that are foreign, not in North America. And so we help them come through that process. So that's a big part of our business. But don't get me wrong, we still run the standard testing and those kind of things in our labs as well. But our goal is to really take that product and understand how far it can go, and put it through its testing and its rigors and mores, so that when we get to the actual lab to do the final testing, we're actually testing it at where it should perform the best. And ideally, that saves the client a lot of money, because most clients show up to a lab. Most labs aren't set up to help a client to say, okay, what pressure do you want to test this? Or how much water do you want to do this? Or what have you. So our goal is to try to do as much as we can beforehand and help them understand what our limitations are, and then help guide them and be a resource, so that when we can actually do the certified lab testing, you get better results and more realistic results. And so Built Environments does that, but also in the education of that, and helping that client or other people that want to get in the industry, okay, what is required? Because it is a gauntlet of trying to understand so many different documents. And, the building code is probably our worst enemy, because it gets bigger and bigger, and it references other sections of acceptance criteria or ASTMs or other reports and ANSI standards. And most people are like, what is all this
they
stuff?
think taxes are convoluted. Just wait till they go through building codes.
Exactly. And it can be very expensive to go and download all its ASTM test methods and standards and specifications and so many different things, where we have that library available that we can help walk through that process.
Library, and also the people like you. You're a building scientist, and let's talk about that. How did you become a building scientist? Now, I don't claim to be a building scientist, because people have tried to say me, are you the building scientist for YouTube? I was like, no. I have nowhere near the intelligence that Jarrett Davis or other building scientists have, like Joseph Stubrick or these other really prominent names in the industry. But I have been diving into material science just through my YouTube videos and just basic research. But you have an extensive amount of experience in that industry. How did you get into that?
That is a great question. I think most of us that get into the building science, I mean, I became a quote unquote building scientist, nearly 2 decades ago. It was before the term was really even coined. And most of us that kind of get in the industry kind of fall into it because there really was no realm for us. If you look at traditional construction, specifically commercial construction, there's always been, the 5 phases of civil, structural, mechanical, electrical, and plumbing, right? But we started to, as our codes, we talk about codes, as they get more complicated and our buildings get more complicated, there was this kind of element that was being missed. And that's really the building science of that building, of how everything looks at everything holistically. And that's really what building science is. We've got to look at the roofs, the walls.
Ties all these different aspects together instead of looking at them individually.
Exactly. So that's kind of how I fell into the industry, was really from a forensic construction standpoint of fixing buildings that were deteriorating or weren't making through their life cycle of even 2 to 3 years because they had chronic mold problems or water problems, and really started backing up and understanding that, okay, you did a manual J calculation on your building, but manual J always oversizes the mechanical system. So we were getting short cycles in the mechanical, or, weren't getting the fresh air that we thought we were. And we started building our housings tighter because we started adding more insulation, and our products got better, and then our windows got better. Well, actually our buildings got worse. And that's really how I fell into the industry, was looking at buildings and homes that were not performing like they were expected to, and understood that, hey, there's a 6th element that we need to look at, and that's the holistic part of our structure. And that's really how I got into building science, and it just kind of morphed from there, and, trial by fire, and that's how you learn everything a little bit.
And you mentioned earlier that you had a brief stint in your career where you were developing building products yourself. And that was, I assume, a big educational experience, because now when you talk to customers, you have both sides of it. You are both the consultant, but you have experience being the innovator too.
Yeah, I mean, that's a great question. So I was an envelope consultant, where, roof walls, waterproofing, air barriers, pulling the energy side, and really the building science side. But in around 2012, I was involved in a code writing process, and actually sat on a code council, and started to see these requirements for continuous insulation. And really, when we started designing projects, we started running into problems. Okay, we've got CI on our walls, or continuous insulation. How do you hang the cladding on this? How do you do that element and actually get our buildings together? And then how much CI or continuous insulation do you do? So we started testing and playing with, okay, what percentage of CI versus BAT? Or do you go all CI and no insulation in the cavity? And really understanding that percentage of aspect ratio, which is now driven into the code. In the energy code, we have that aspect ratio. Personally, I think the aspect ratio isn't high enough. I think you should higher percentage of CI than you do of BAT, because it keeps you out of trouble a lot better. Should be more of a 70-30 ratio rather than the 60-40 ratio as we see in the code today. And I think we're going there. But so in seeing that process of the code change, I developed basically a structural insulated sheathing. And it's a product that's fairly well known today, as after several years that company grew to an extent that was large enough that was probably beyond my scope as just an ordinary building scientist and running a manufacturing company. But so I did end up selling that company to DuPont. And so that product is called Armor Wall, and now DuPont represents that product in the industry.
So when you talk to clients, you understand their frustrations with bringing the product to the market and everything that they have to deal with all the code requirements and the testing and everything. Their frustrations are not just falling on deaf ears when they talk to you.
Yeah, I mean, I thought that, okay, I knew codes pretty well being a consultant. I knew what products were and their data sheets and how to understand the ASTM test methods and all that.
But it's the theoretical versus the practical, right?
There's no, as they say, if you really want to understand something, you've got to teach it to someone. If you understand enough to teach it, then you really understand a subject. And I thought I understood it enough. And so a buddy of mine came to me and said, hey, I got this idea. Tell me how you bring this to market. And I'm like, you're right. I don't understand this enough. So, excuse me. So I had to go learn really what the test criteria was. And especially for a product that didn't exist, it was even harder. So you had to develop what we call acceptance criteria to test your materials to something that you're replacing in the construction side. So that that trial by fire was unique and very expensive. And that's a big reason why, built environments existed for a while with my partner, Steve Doggett. But I really brought in the practicality side of materials and understanding that testing process and how to do that, because I went through that process and I know exactly what those clients are feeling. And it's a hard road.
Oh, yeah. But you talked about the material science aspect of it. We talked about building science, but Built Environments, the company, also does product design, product testing, code consulting, R&D, and industry education. You have quite an extensive library of educational videos on YouTube, and you're very charismatic. You explain things really well, because this is such a complicated topic that can go over people's heads. So your ability to break it down into the simplistic forms, into something that the layperson can understand, that's truly an art.
It is interesting. And Steve and I, Steve's this PhD, way smarter than I am, and really understands the material science of things. But I bring the practicality, the construction side of, okay, how do we actually use this and how do we do this? And really that's our goal, Belinda, with Built Environments and those videos that you mentioned, is to pull the curtains back and show, okay, this is really like, the experience we were able to invite you to. This is what a fire test actually looks like, because most people don't get to see those. And most manufacturers running testing are always doing it behind closed doors. So the reality of even most users, contractors, architects, designers, never get to see an E119 test or an hourly rated wall test, or what a WRB is, and really kind of how low performance requirements it takes to be a WRB. And so that's really the goal of Built Environments, is to open that curtain and say, hey, here's the test, but we do what we call rogue testing. Now let's really take that to a true condition of what happens when we draw our buildings perfectly on paper every time, right? There's never any issues. But unfortunately, in construction, there's always a scratch your head moment of, oh, how do I do this? And sometimes it's not done perfectly, or there's defects. And that's really when a product is put to the test and when it needs to perform. And that's our goal. Yeah. Is to get to that point prior to it getting to the market.
So that's a very interesting point. Drawing back the curtains, like Built Environments, just drawing back the curtains, because we all know that I compare all these suburban homes that are being put up all around the country to Hummers, like the gas guzzling Hummers. They're built in, they're just terrible quality, as fast as they can possibly be put up. There is a complete lack of building science and appreciation for well-built structures in this country. And what y'all are doing by making building science cool, making it accessible to the public, that's helping spread more education, and in turn makes people aware of the importance of well-built structures. So it's going so much further than just material testing or product testing, but it's going into the realm of just public education into the importance of building better. So I think it's really cool.
I mean, you hit the nail on the head. That's exactly what we're trying to do. My favorite moment to do in the lab is when we're doing a test wall or a mock-up for a construction project or something, and we have the crew come in and just build it. And we don't say anything. It's like, build the wall like you're going to do it. And we watch and we see, okay, what, are they reading the install guide from the manufacturer of how to put the products together? And I'll tell you, I've seen, hundreds of thousands of walls built in my career, and rarely are they built to what the manufacturer specified. And that's a big, key point for us, is to educate those trades. And so my favorite moment in the lab is now we have, several folks that work for us in the lab, and we brought in folks that have, 20 years of building experience, 30 years of building experience, and they build their first test wall, and I get to walk out and say, nope, that's not how it's done. And you can't use slap staples. You have to use button caps. You have to do this, and that's not the right frequency. And because those little things matter, and they're like, well, I don't understand why that's going to matter. Okay, well, let's put it on the test wall.
Let's show you, yeah.
Yeah, exactly. So we put it on the test wall, and you start running, 60 mile an hour winds and water at it. It's pretty evident pretty quick. And just that light bulb goes off, and that's my favorite moment. It really is.
Yeah. So I noticed when I was going through your website and your client list, one of your clients is Vantum. And I actually had the CEO of Vantum, Chris Anderson, on my podcast earlier this year. And he when he was talking to him, he talked about magnesium oxide panels, and that was the first time I had heard of that. I'd like briefly seen it on LinkedIn, and I didn't understand what it was, what it's composed of, its uses, its advantages over drywall. But you have a lot of experience with magnesium oxide panels, and the testing that we saw in Bryan earlier this year, that was actually a fire testing of magnesium oxide panels. So let's talk a little bit more about that. Like, what exactly is it, and why if it's so much better than drywall, why hasn't the industry adopted it on a more like wider scale?
Oh, wow. Well, your first question is you're asking the construction industry to change, which is one of the hardest things to do ever. And I think MgO, magnesium oxide or MgO, has its place. Is it a true 100% replacement for gypsum or drywall? No, and I think that's a big misnomer. And a lot of people try to push it. It's always better than gypsum, and that's not, quite frankly, always the case. And I think that's been a little bit of the problem. A big issue with MgO has been just general market acceptance. I first found MgO probably in the early 2000s, so quite a bit of experience. Wow. Yeah, actually on a mission trip and they were using it as a stucco type product. So it was pretty
almost
unique.
Like a plaster
alternative? Exactly. Yeah, a rendering. Yeah, that's exactly right. And in a lot of parts, so magnesium oxide, magnesium is the most common element in the Earth's surface. It's just getting the purity and the reactivity right after it's calcined. And there's different methods of calcining magnesium oxide, over a light burn or a dead burn, and just different varieties. But so there's different reservoirs of magnesia, or it's called brucite, is actually the mineral as it's mined around the world. And the most common place of that, because the largest deposit of it is actually in Asia, in northern Asia, in northern China. And so the Chinese first started making boards with it in the 90s. And there were some problems. It is a chemistry thing where you have to get the ratio done correctly. And if you don't get it done correctly, you can have disastrous results. And so there's that kind of black eye out there that folks still get, what I call the keyboard commandos. We'll go out and Google, issues with it. And there's a very prominent case in Northern Europe and Denmark that happened in the 2010, 2012 era. And there was a very, very bad result that occurred. And so that's where a lot of people go with it. And that's true. But so magnesium oxide isn't meant to be continually exposed to the weather, right? So it needs that WRB and that weather resistance barrier. In that case, it didn't have it, so they had some corrosion issues and some what they call crying, which is really a bad ratio and formulation of material. So with Vantum, I think, first of all, their modular type construction methodology is phenomenal, and what they want to do with housing. We talked about housing briefly, and our big issue is the labor force, and I think modular construction should have
potential.
More. Absolutely. I think it should have way more market share than it does. But again, I think the general home builders are sticks, and that's what they're used to, and they know how to work. And a lot of it's just lack of planning and be able to foresight and do modular prior to that. So Vantum saw the use of new materials, and as we look at a lot of technologically innovative manufacturers and developers, they're starting to adopt the modular construction. And Vantum understood, hey, MgO has a place here, because when you get into modular, the rigidity of MgO versus a gypsum, that's when you start getting the structural elements really come into play. The fire ratings from MgO to gypsum are actually quite similar. But the rigidity of MgO is similar to an OSB or a plywood. So you're getting the fire rating of an hourly fire rating from gypsum out of a material that cuts and acts like a wood-based material. But then when you get it, and it does get wet, not like continuous exposure like I mentioned before, it needs a WRB, but let's say if it's in the inside of a building and it gets wet, then it doesn't have any negative results. It doesn't become soft. It maintains its structural rigidity. And if you think your building is never going to get wet, you're 100% incorrect, because we wet all of our buildings every single day. We just call them painters, right? So we have to understand how our buildings dry and how our buildings are going to do this. So you take a material that can withstand some water and the absorption rate, but then dispel it at a remarkably fast rate and maintain that structural rigidity has a great place in modular construction, because we can hold our walls true and square and in plane while it's being shipped and it being erected. And that's an innovative material.
That's a very good point, the transportation aspect of it, because I've seen so many. I've visited quite a few modular companies over the last 2 years or so, and it's a lot of them talk about all the cracking that occurs during transportation, and then there's no way to resolve it other than just bring in labor force to the job site, and it's just kind of defeating the purpose to fix all those cracks after everything has been installed. So the rigidity that you're talking about with magnesium oxide could potentially eliminate that extra work that needs to be done after installation.
Yeah, I think so. I think there's still some technology that needs to be advanced on the mud and the mixture ratio of the seams and stuff for sure. But the sheet good product has so many positive attributes that it is starting to be known. And you look at, a lot of the industry players of magnesium oxide are becoming bigger and bigger. When I first learned about it, in the early 2000s, it was what I call two guys in a pickup truck. And that's really what gave it a black eye, is folks were importing material and it was coming straight off the container and going straight into a job site. And that's really not the way it should be handled. You've got to have a quality assurance verification measure to do that. And that's a big part. What I'm trying to do, just in MGO particularly, is develop ASTM standards. I'm actually the technical chair for the ASTM task group for magnesium oxide. I'm also the ANSI chairman for the ANSI standard that we're developing through ICC right now for MGO. I sit on numerous committees and numerous efforts for magnesium oxide, because I do think that product has so much potential, but we've got to get it written into these test standards and these methods so that we can actually use it. And that's the big challenge that it has.
I mean, you could find bad press about any material, right? Like when I looked into drywall a couple of years ago, there was some pretty bad drywall products that were imported from overseas. I think 20 years ago or so. I'm not exactly sure.
Probably about a decade ago. About 10 years ago. Yeah, in Florida.
And that caused some bad issues, but no one considers that when they put drywall in their home. They just accept it. So why not understand the reason why magnesium oxide didn't work the first time, and understand that we have learned from those mistakes, and let's just give it another chance. Yeah,
absolutely. And again, I'll say it again, gypsum has an absolute place because it's cost. But when you get into things where you're looking for structural elements, such as shaft walls and stairwells and elevator shafts, where you actually want to attach a material to it and have a wood-based product but has that fire rating, that's where MGO is going to shine. Its impact resistance is so good that's a great place for a product such as MGO.
Let's talk about the fire testing of MGO. And you said it is comparable to drywall, but the details of the fire test, because I mentioned it at the start of this podcast, it was an extremely dramatic, extremely cool experience. But let's talk about it. How are these panels built? And let's talk about the details of the fire test, like the temperatures that it's subjected to, and the water pressure test, water hose that it's hose stream.
Yep.
Yeah, let's talk about that.
Yeah, sure. So it's, as you mentioned, we met in Bryan, Texas, which is ICC NTA's lab. They're a partner of Built Environments. We work with them quite a bit, and we have videos. I think you have a video coming out about that day as well for yourself, and then we have extensive videos. We shot a whole series where we were there for a whole week, basically, on E119 hourly rate, and as well as NFPA 285, and that'll be available in Built Environments. But
those two names that you mentioned, can you elaborate on those two fire tests?
Great question. So ASTM E119 is a test method for doing hourly rated wall testing. It's basically a clamshell furnace that you take a wall that's approximately 10 foot by 10 foot and put it on the face of the clamshell. And then the inside of that clamshell is gas, and it's ignited. And we measure the temperatures of that gas, and it increases throughout the period of the test. So, you typically run for your ratings that you're going for a 1 hour, 2 hour, 3 hour, et cetera, based upon what you're trying to design for the wall assembly. So that test, you can do loaded, you can do non-loaded, where it's a weight-bearing wall or non-load-bearing wall. There's a whole different varieties to it, and there's a UL 723 as well, which is the same. UL kind of has their own standard, and that's a big thing in the industry where architects, for example, used to be, even in my design office, when you go in an architect's office, you go to the library, and they always had like 3 full shelves of those orange books of the rated walls and floor and roof designs, and everybody thought, oh, it has to be a UL number. Well, actually, no, it can be an E119 test is exactly the same for the most part, and the code actually says E119 or 723, because UL is just ran at UL's lab, obviously. So we use these other test labs in E119, and that's the wall that you were able to witness was the 1 hour wall or 2 hour wall. But essentially, we put it on that wall for an hour, and it's all counting down. And we're looking at deflection of the wall, because as that wall gets hotter, it will a lot of times go into the furnace. And then when it's about to rupture, it'll come back out of the furnace. So you see the deflection of that wall move as it goes through the age of the test. Especially if it's load bearing, you'll see it a lot more. But then once the test off, as part of that standard, you think about all fire testing, what we're trying to do is protect the building, protect the occupants of the building, right? We're trying to allow people time to get out of that building if a fire does occur. So E119, we're simulating, okay, if a fire happens, let's say in this one apartment, it's got at least 1 hour before it goes through the wall into the apartment next door. So we need 1 hour for them to get out of the building. But what happens in about an hour, and generally the response time is a little better, is the fire department shows up, right? So when the fire department tries to put out the fire, what we don't want to do is push that fire from one wall to another wall and into another room and continue that fire. So after the completion of that 1 hour, 2 hour, what your duration is, you take that wall immediately off the furnace and you turn it around so that the side of the wall that was exposed to the furnace now gets subjected to the hose stream, which is essentially a fireman's hose. And we're shooting that with water for a period of time based on the length of the test, whether it be 90 seconds or 2 minutes, and it varies based on the duration of the test. So we have to withstand not only just the 1 hour, 2 hour fire from coming through the wall, now we have to withstand that water from coming through that wall as well. So it's incredibly unique, and a lot of people don't understand that that's part of the test and how to do that. And there are other ways to do that. You can do a half burn to go back and retest, and that gets into the nuances of the test standard and so forth. And that's our goal, like we mentioned, is just show that test to say, this is how this really looks like, because that chamber, that clamshell can get, we're generally looking in the 1700 degree range.
Wow. Oh my gosh.
Yeah, fire's hot.
That's true. But how many of those tests have you seen in your career?
Oh, wow. E119s, yeah, definitely into the hundreds. But we have folks that we work with, and you'll see in the video, Mike Luna, who actually built the lab for ICC and now runs a consulting company. We work with them quite a bit as well. There are folks that specialize just in fire, and that's their whole career. And that's part of the challenge with being a building scientist is, I may not be the world's foremost expert.
Trades.
Yeah, exactly. But I know who to call. And so Mike and ICC, NTA, and those guys are definitely resources for us. And you could call them directly. You could not call it and say, hey, I want to go do a fire test. Hey, sure, absolutely. But again, they're going to run the test. They're not going to tell you should it be loaded and what those pressures need to be and all those things. And that's where we kind of come in.
So you act as an advisor after the test is complete. So you tell the company or your clients whether it failed, whether it passed, what exactly went wrong, what needs to be changed in the wall assembly or the material itself.
Right. And that's a big thing. So a lot of these tests are ran like in different facilities, and there's several different fire labs around the country, or even around the world. But a lot of these manufacturers are not necessarily domestic, so they can't be there to observe. They might be able to, watch through a
webcam or something.
Yeah, exactly. But you don't get the full aspect. So we're actually there looking, and you'll see us during the test, a lot of times we're looking offside, we're looking inside the chamber, and that camera is not going to show you that. So we're going to also help you before you burn. We're going to say, well, if you burn this one wall scenario, you can get these other scenarios with it. Because when you test, and this is a misnomer of testing, and this is really our big thing. When you test, you want to test your worst case scenario. Because if you pass your worst case scenario, well, guess what? Your better cases where you have less combustion or better structure, you can get those. And that's where we really help the clients to understand what is that worst case scenario. But there's a fine line. You go too far, and these tests are expensive. An E119 test can run anywhere from $15,000 to $30,000 depending upon the complexity.
Oh my gosh. Wow.
Absolutely, absolutely. So it's very, very expensive, and to a client, that's just for the test, and that's just for the lab. But you also have to calculate shipping materials in. You should get your material witnessed before you test it. You have to pay travel time. You have to do the construction, and then you have to get the report. And what do you do with the report? So these tests are not cheap. And our goal is to get the desired results the first time. So we can do smaller tests. We have a small scale furnace in our lab. So we do a lot of small scale testing prior to it actually getting there.
And
that's a big part of
lab located?
Great question. So we are in Wilmington, North Carolina. We're on the coast, and we're specifically on the coast in Wilmington because we do a lot of what we call hot, humid climate research, where we actually have some test huts and structures around the area where we're actually monitoring how those buildings perform. So that's a big reason why we're in Wilmington. My partner, Steve Doggett, actually Built Environments has been around for 25 years, and Steve started it, shortly after. He was a professor, so he's PhD, again, way smarter than I am. But he started Built Environments and has been doing that for a while. And I joined him about 2 years ago now, and he was in Minnesota. And I said, that's great, but that's cold. That's all the Canadians kind of have that figured out. So we moved, and he and I both moved to Wilmington to build the lab here because of its hot, humid climate location and very close to the coast and that coastal research. And that's a big part of where we focus of in situ testing and things that we do.
How large is the team at Built Environments now?
As of today, I think we're running about 12 or 13 folks that are full-time for Built Environments. And we have some other contractors that we rely on and things as well. But we have an architect, engineers, again, lab techs and professionals, and some marketing folks and admin, and then Steve and I, they're probably just drive them crazy all the time.
But it sounds like the personnel that you have at Built Environments, y'all advise people based on all this knowledge that you have up in your brains and all this experience that you have gathered throughout your careers. Have you all tried to codify that in any sort of way and turn that into a software model so that, because you don't need to be, Jarrett doesn't need to be at every single fire testing, you can have a substitute or even an AI Jarrett that's there that can do the same sort of analysis. I know there's a lot of human aspect involved and a lot of variations that only the human brain can comprehend. But have you tried to codify all the knowledge that you have?
That's an interesting question. I've been involved in a couple of those AI type experiments, and the problem is you have to teach it what's good and what's bad, and it takes so many of those examples, and you have to explain. It is very subjective still, and I don't know if you're ever going to get rid of the human element of the test. Sure, there's okay, you went too hot, you failed. You have too much deflection, you fail. But what do we need to change so that we don't have that for the next time? And that's the hard part. And I don't know that we can get that to AI yet. I mean, I'm sure there's technology and there's folks out there that are working through that, and they're probably going to come along and probably be able to do that. I don't know it's going to happen in my career.
Maybe that's the next thing you can tackle, a forensic scientist AI model. I mean, why not? You have enough experience.
Maybe someone's gonna have to be smarter than I am to do that. That is not my expertise for sure. Every man's got to know his limits, and that's definitely mine.
So throughout your career, when you did all these fire testing of building products and even assemblies, was there one particular assembly that really surprised you in a way that you didn't expect it to pass a hour-long fire test and it passed a 2-hour fire test or something pretty drastic?
Probably not in E119 in the fire testing side. The more surprises I've had would be NFPA 285. And in 285, you got to see that wall as well, and there's some processes coming out of that and videos of that. And that's a multi-story barn. And probably the most impactful one of those I've seen is one that just went off like a Molotov cocktail. It actually failed rather miserably, and really, what you have to understand with 285, we're trying to protect from a fire. E119, we're trying to burn through the wall. 285, we're trying to burn up the wall. So all these multi-story high-rise buildings that are occurring and all these fires that are happening, really around the world, and that's really what 285 is trying to do. So we're trying to if that fire breaks out in that kitchen of that condo or townhouse or whatever it may be, and goes out the window and burns up the wall, we don't want it to lap up above the fire-rated wall to get in the room above it. So we had an assembly that we thought was pretty good, and made out of limestone, and everything was pretty robust and had a great combustion rating, and did really well in E84, which is a smoke horizontal burn test. And I thought it was going to be a no-brainer, no problem. But reality-wise, what we found and where we realized we had to be careful was in these rain screen assemblies, and rain screens are becoming more and more popular. Especially in commercial construction, and it gives the architect the ability to design these beautiful facades and aesthetics, which are phenomenal. But the problem with a lot of these facades is they're held together with an adhesive and a mastic tape on the backside of that panel. And once the material above the window head deteriorates over that portion of the fire in 285, it gets behind that panel. And a lot of that adhesive is, what we know now, is essentially like napalm. And once it ignites, it's a very fast fire to the top, and that's a bad day. So that was probably one of the more monochromatic, and that was over a decade ago when I saw this one. So we learned a lot as far as how to deal with that cavity and understanding the depths of that cavity, and that's a big part of 285, and that's still in a lot of conversations. Of can you take that cavity where it's an inch and a half and make it 12 inches? Well, not always, because now you got a chimney and you add more oxygen. Or can you reduce it down to a quarter? Well, no, not always, because now you're giving that fire, you're driving it by pressure up that. I mean, so 285 is a complicated beast.
Wow. Oh my gosh, there's so much. There's so much complexity to all this. There's just not an easy answer. So I take back what I said about turning this into an AI model. But maybe it can be done. But when you're explaining all this stuff, a question came to my mind. You have an industry education aspect to built environments. Mm-hmm. When you go through these tests that either fail or pass so successfully that your client wants to keep it a secret, how do you balance that? Because that can sometimes be contradictory, because you want to tell the industry, hey, this doesn't work. As an industry, as a whole, we need to come together to find a better solution. But your client probably doesn't want that to be shared.
Right. Yeah, that you're hitting on a difficult subject, and we deal with a lot. We do a lot of litigation support as well, where we're testing things for litigation, and we can't publish that, obviously. So when we do have tests that aren't a pass, we kind of are very careful about what we ever say and what we ever do. And in our presentations or education process, we typically, and just like this podcast, I never name manufacturers. And we try to keep that out of it. And we're very careful about what images and things that we show.
But you can still take that experience to the next one, and maybe not divulge your particular client, but in the back of your mind, you can indirectly tell your next client or something, that particular wall assembly will not work based on my experience. Right. Maybe do it a different way to make it work. Yeah.
And that's a lot of what they're paying for, is that experience.
Yeah.
Right. Of our knowledge and be able to do that. So sometimes, and I'll be honest with you, you learn more from a failure than you do a pass most of the time. So some of those failures, and sometimes some clients test thinking they're going to fail. And absolutely to try to get data. Now, those are typically more sophisticated clients that have larger budgets because they can afford to run those tests, because a 285 test is
$30,000. That's fine. Let's test
this out. Yeah, that's just a drop in the bucket. But no, 285 testing is very expensive. And like I said, there's a lot of consultants out there, not just Priest, but, very many other consultants out there. That's all they do is fire consulting. But we strive to educate the masses, and more when we're educating the masses and we're doing those processes, I really want to make the designers and the contractors and the building owners aware of this test requirement and what the reason is. I mean, most of our tests that are out there are developed, and we have these numbers and these tests, and like, okay, great, I got to abide by this. I want to make you understand why it matters. And understanding the 285 of burning up the wall has a huge predicament. Before, several years ago, we started building more plastics in our buildings, and that's a big question about the fire. And before the last really probably 7-8 years, people didn't pay attention to 285 because we didn't have continuous insulation, especially the plastic, and we didn't have these spectacular fires that we see in Europe and Asia and even the U.S. of recent. So 285 has actually been the building code since the 80s. But no one actually really knew that, never paid attention to it, right? Until really CI hit the market and then plastics and foam plastics in Chapter 26. But it's been there for a while.
Speaking of other countries around the world, is there one particular country or region that has far more stringent fire codes than the US does? Like, do you as a building scientist constantly have to look at what Europe's fire testing is doing, a material testing, or Australia or China or Asia?
Yeah, that's a great question. And every market's unique, and that is part of the challenge. Like I mentioned with some of our manufacturers we work with that are based in Europe or Asia or the Middle East, coming to the U.S., we're typically done by the International Building Code and ICC. But there are other markets such as the Middle East that will follow ICC and other parts in Asia and things. But everybody kind of has their own twist on it a little bit. So we have to go back and look at those tests. And if you there's a similar test that's an EN standard that's very close to the NFPA 285, but it's not exactly the same. And even going from the U.S. to Canada, that test differs on 285. Now, our E119 hourly wall ratings, that's pretty close, pretty similar throughout the world. But if we look at other worlds, the problem we run into the most is a lot of other places in the world allow a semi-combustible material, whereas we don't allow that in the ICC. So it's either combustible or not. And that's how you get your A1s, A2s, A3s in Europe and things of that nature. And the U.S. and specifically ICC and even other countries that adopted ICC, that option isn't there. So that gets into some gray areas very, very quickly. And that's kind of where MGO falls, actually, a lot of places.
Into those semi-combustible materials, yeah.
Well, there's a big stink on that, and that's another ESTM E136 we won't get into on this one because we'll be here for another 5 hours. But yeah, I mean that's a challenge where how do you take a material that essentially is made of rocks, but if you put it in a furnace that's 750 degrees or 750 degrees Celsius, things happen at 750 C. That's pretty darn hot.
That's true.
So.
Oh, well, this was such an educational discussion, Jarrett. Thank you I mean, we could talk about this for another 3 hours, like you said, just about every single fire test and materials science test that you're going through. We definitely have to have you back on the podcast in the future. Absolutely. To talk about some other cool materials that you have been testing and experimenting with. But I would love to end our discussion with some advice that you would have for a young professional that wants to help the industry build better, that has identified pretty early on in their career that there is a need for us to maybe use more innovative, better building materials, or just a need for better continuous insulation. What advice would you have for them?
That's a great question. The biggest advice I can give is get involved. A lot of these industries have young professional programs. Don't be afraid to get involved. I mean, it's just like an ASTM. It's very daunting. You go there and there's these people that have been there. Most people are decades older than I am, but you show up and it's like, oh my gosh, there's all this knowledge here. But you go into a room and half of them don't know what they're talking about either. So don't be afraid to get involved. I mean, a lot of this in the industry is, hey, if you have an idea, be bold and do it. But as far as products and things go, I think the biggest thing of development side is a product that can serve multi-functions. It can do more than one thing. And that's what the market needs. Again, we talked about, modular construction and our labor pool. If we can have products that do more than one element, that's got the biggest function to actually change construction, in my opinion.
When you say a product, you're talking about a particular building material that can serve more than one purpose?
Yeah, I mean, it can be a mechanical system that also powers electricity somehow. I mean, it can be a system that has a built-in WRB or water-resistant barrier. It can be an insulation that's also functional for air barriers and modifies for fire. And those are just ideas that randomly came off the top of my head. So, a young person that wants to get involved, do it.
You think like the fewer... There's a problem right now in our wall assemblies where there are too many components to it. So you think the simplification of that could be something that's game changing for the industry?
Absolutely. There's an old joke out there. If you look at the old castles or old churches from Europe in the 1000 era or something, how many layers were in that wall?
Rocks and mortar.
Yeah, one, right? It's rocks. But now you go look at our walls now, and everyone wants to build lightweight construction, right? We don't build schools out of CMU anymore. We put steel studs up and all these facades and rain screens. Then you got CI and WRBs and air barriers, and then, oh my gosh, you have vapor, and yeah, it gets complicated really fast. So there's all these layers, and there's so many potential to get something wrong that that's the challenge. So a young person, they can think outside the box. And I love young people because they haven't been molded to, one of my favorite jokes that Joe Stiebrick used to tell is, the 8 most expensive words in construction. That's not the way my daddy used to do it. Right. And change is so difficult. And I every time Joe tells it, I think it's hilarious, especially, being here from the South. But I love young people because they're not molded to, hey, that's the way we've been doing it for my whole career. That's the way we're going to do it. And I think that's such a terrible mindset. And that's the hardest thing in construction is change. And that's why we're so far behind. Our production ratios are lower than they've been in, decades as far as the amount of units we can build in a certain amount of time. and that's going to be, ultimately that's the reason for a large housing crisis.
That's
not to mention the cost, but it's time.
Yeah. Well, that's excellent advice, Jarrett. Thank you so much for explaining all those fire tests to us, and thanks for sharing your advice with the young professional industry. Again, need to have you back on the podcast so we can dive into other sort of fire tests and material tests. But thank you for joining us this time.
Yeah, Belinda, it was great. I encourage anyone, if you want to reach out. I'm an open book. We have our videos on our Built Environment site, but also you can find me on LinkedIn. Very easily to find me there. Go to the Built Environment site, shoot us a note. We'd love to have interaction. You have ideas, you want to see some tests? Hey, let us know. Because it's not just fire, but we haven't even gotten into water and air and chemical composition or sealants, and there's a whole litany of things. But would love to hear feedback and what people want to see, because our goal is to open that curtain.
Gardens, yeah. Okay, so we need to have a series, Jarrett. We need to have a series on sealants. We need to have a series on water testing, all this stuff. You definitely need to come back. And I'm serious about this.
We may need to see how many people actually watch this first. We're like, that's a blowhard. We don't want to listen to that guy. No. You're very charismatic and excellent explaining complex topics. I really appreciate it. I enjoyed. I had a great time, and I would love to do it again. It's really quite fun.
Yeah. Thanks, Jarrett.
Yeah, thank you.